Number 21, econometrics in practice. So today I am going to talk about logarithmic function of y and or x. Why do we take log? First of all, we need to understand this. In general, we take log of a function if data may become linear from non-linear. Data may become homoscedastic from heteroscedastic. Heteroscedastic data may become homoscedastic. Data, non-normal data may become normal by using logarithmic function. Here we are going to see log of dependent variable or log of x. In our previous video 20 we have discussed a polynomial regression function or nonlinear regression function in variables. So another important thing, when we take log of variables and we take the difference, it may be expressed very closely to the growth form. For example, log of y 2021, log of 20 GDP minus log of 2019 GDP, that's almost same as change in y over that is almost equal to y20 minus GDP in 19 divided by GDP in 2019. So it's almost equal. That's what we are talking here. If the time period is short, then it's very close approximation. If time period between two values get large, for example y20 and y2010 GDP, then it may not be that good approximation. So here we are going to discuss three cases. In each case you have a different interpretation of a coefficient. yi equal to beta naught beta 1 log of xi. So in this case a interpretation of beta 1 is different. Log of yi beta naught beta 1 xi, different interpretation of beta 1. Log of yi log of xi, different interpretation of beta 1. And moreover, when we take log of y and you have log of y here, their r squares are comparable because total sum of square is based on log of yi. But log of yi and log of yi, their r square is not comparable because total sum of squares in this case is based on yi, and in this case it is log of yi. Whereas we know numerator is always expanded sum of squares or regression sum of squares. So this changes from this first form to another one. So if your dependent variable is not of the same nature, two models r square is not comparable. Now let's go and see the first model, linear log. In this case we take log of x only, and the rest before and after that we have discussed already in our previous videos. It's almost beta 1 is equal to change in y due to percent change in x. Change in y due to percent change in x, and this will be interpreted as delta y over change in percentage change in x. A 1% increase in x is associated with a 0.01 change in y, beta 1. Delta y will be equal to 0.01 beta 1 unit. So that's how we increase, how we interpret it. For example, we take log of income. So it means that if income is changed by 1%, there will be an increase in test score by 0.642 units. R square will the standard error, they have standard interpretation. So here you have log, linear log and cubic log. So you see how close approximation this linear log is to cubic log when you have district income and test score. So by taking log, you have reduced a third degree polynomial, x1 square, x1 cube. Instead of that, you have just taken log of x and you have regressed y on log of x. So it's simple. So and it's simple to interpret, and secondly it consumes less degree of freedom. Log of y equal to beta 1 x, so its interpretation will definitely change by the percentage change in x, the y divided by change in x, and that means that 1% change in x, 1 unit will lead to 100 beta 1% change in y. So you can look into these bullets and you can understand it. Next one is the most commonly used and very simple to interpret. That is beta 1 is elasticity. Percentage change in x leads to beta 1% change in y. That is percentage change in y due to percentage change in x. This is elasticity, and if we remove y and x from here, that's the slope. So there is a difference between slope and elasticity, and if you take y bar and x bar, that is elasticity calculated at means. So that's a 1% change in x is associated with a beta 1% change in y, and beta 1 is here elasticity. Beta 1 has the interpretation of an elasticity. Here 0.0054 554, 1% change in log of income leads to 1.000554 change in test score. That is 1% increase in income is associated with an increase of 0.0554% or 0.000554 change in y. That's 10% increase leads to how much change, 15% change in leads to how much change. There are some issues when we do forecasting for this based on log of test score, and then if we need to convert it into its original units, that is test score. So there are some complications. We will not talk here about those complications. Here you see that district income and log of test score. District income and log of test score, here log is better fit than linear log. Yes, that's the case. So I'm going to wind up 3 cases we have discussed, and your standard your statistical influence and all those things remain same, except that your R square is not comparable when your dependent variable is not of the same form. There are some other nonlinear regression functions. These are basically nonlinear in parameters, and nonlinear in parameters are different than nonlinear regression functions in variables, because your estimation method and other things will also change. Nonlinear least square, method of maximum likelihood estimation, and all these things will come in, and we'll discuss it in logit probit models and at some other places. Thank you for watching. Take care.